started. Thank you everyone for coming to the Colloquium. I'm pleased to introduce James Ruppert. James is an assistant research professor at Penn State University. We actually know each other from back in grad school. James got his PhD in 2015 from Colorado State University, so we overlapped there, where he worked with Dick Johnson. He did a lot of interesting research on the diurnal cycle and tropical dynamics. After his PhD, he did a postdoc at the Max Planck Institute in Germany, where he was actually under a NSF Atmospheric and Geospace Sciences postdoc research fellowship, as well as an Alexander von Humboldt postdoc research fellowship. So he was there for, what was it, two and a half years before coming back to the States. And now he's over at Penn State, and he does a wide variety of research, lots of interesting research in the Diurnal Cycle. He's worked with MJO, gravity waves, and most recently, tropical cyclones. So with that, I'll let you take it.
So thanks very much, Steph. Really grateful for the chance to be here and talk to all you guys about the work I've been doing. And I hope I'm speaking up enough. Can you guys hear me in the back? Do we have to mic me? Okay, cool. Yeah, so this is some work I've been doing on trying to assess the role of cloud radiation interaction in tropical cyclones. And a lot of my work, ever since my master's, has actually fully involved the diurnal cycle. And I think this is the first study that is actually non-diurnal in sort of an essential way, because it's dealing specifically with infrared long-wave radiation, which fundamentally is not diurnal. So the background picture here is Hurricane Maria. That's sort of the star of the talk I'm going to give today, in essence. Right, so shortly before it makes landfall in Puerto Rico, which is completely shrouded by cloud here. And just some sort of statistics for right around this time, close to its peak intensity. So I want to do sort of a brief thought experiment using this image, which is a visible satellite image of obviously what very clearly to your eyes is a very intense tropical cyclone, right? So imagine the idea of a transparent hurricane, where, and this is sort of a bizarre idea, you imagine you can identify the hurricane not by its very clear white cloud deck, but perhaps by the very strong winds you can see churning up the ocean surface, or ravaging the land surface as it makes landfall. That's kind of a bizarre concept, but I would actually say to that our conceptual understanding of tropical cyclones, by and large, and in fact the way we run our toy models of tropical cyclones, by and large, is of transparent tropical cyclones. And what I mean by that is that the radiation, the radiative heating of the atmosphere out here is very similar or identical to the radiation in the model that's being imposed here. And so by virtue of that, there's no radiative coupling to the cloud patterns of the tropical cyclone. And that's how we've thought about tropical cyclones for a long time. So we're asking the question of whether or not that's sort of okay to think about that in the real world tropical cyclone forecast context. So there is sort of a clear reason why you could come to the assumption that radiative forcing is negligible. And what I mean by that is sort of from a basic scale analysis. So shortwave or solar heating, so that's the heating of the atmosphere due to downward shortwave insolation. And then long wave heating, it's a cooling, so it's a negative. These are both on the order of Kelvin per day. Shortwave positive, long wave generally negative, not always. And generally on the order of a Kelvin per day. Latent heating, on the other hand, is at least an order of magnitude larger, very typically. And it could be very easily 2 orders of magnitude larger, up to 100 Kelvin per day, in a very strong convective core. So you can imagine from that, if this is that strong, that's probably dominating the energetics of a tropical cyclone, so why do we even care about this? But the point is, even though the primary energy balance and circulation balance in a tropical cyclone may be dominated by latent heat, and by extension surface fluxes, fundamentally, that does not require that the formation of a strong TC is driven by the same process. Right? So that's the point here. And that's why we move on to our objective. It's to assess the role of radiative feedback in tropical cyclone genesis and rapid intensification. in particular in what we hope is a realistic context. And I'll get into that in a moment here. So I want to first make some acknowledgements. So my co-authors on most of the work that I'll be covering today. So Allison Wing, Xiaodong Tang, and Erica Duran, you may know her as Erica Navarro previously while she was at Washington. And then for me, my luminaries on this subject. So there are a handful of them, and I'd say most important for, in particular, luminaries for me on this particular topic, on this research question. A lot of people have thought about this question come before me, and in some cases before I was born. So Bill Gray here on the left, and no, that is not a grad student on the right, that's Fuqing Zhang. So Fuqing Zhang, who also is perhaps one of the most influential scientists of his generation in predictability and gravity waves, but also leaves a massive mark on me for how I approach this particular research question. And I'll just mention here, so Dave Raymond and Rob Fabell are perfectly alive and well. I include them on this list for the fact that they've had very, very important insights to the way I think about this problem. So, I'll briefly touch on this first bullet point here. So what is the role of radiation in the basic state? So I want to start from sort of a large scale understanding and sort of our zero order thinking of the role of radiation in the large scale in the context of the tropical climate system. And then we'll get into the question sort of more at the heart of the problem, is cloud radiation feedback important to storm scale dynamics? So for this first question, we're going to go back to a very original figure by Manabi and Strickler. So they run a single column model. So it's a single column climate model run for a very long time scale. And they predict the temperature trend you get through the atmosphere based on certain processes being included or excluded. So in sort of the cartoon sense, into the climate system, we have shortwave flux, which the first order, some will assume, reaches the surface. And these vectors, in an equilibrium sense, should be equal to one another, right? And from the surface, leaving the surface, the long-wave flux, no atmosphere, this is an idealized sort of thought experiment, these vectors have to equate to one another. But we know that's not in actuality the case because we have a greenhouse atmosphere. And we think of long-wave as a cooling, but compared to the context of a no-atmosphere situation, this is in some senses sort of bottom-heavy warming. And what I mean by that is that by including this greenhouse atmospheric radiative forcing, you end up with a temperature profile that's absolutely unstable with respect to vertical convection. Now, in their single column model, they include a simple parameterization to include convection by either forcing the lapse rate to be dry adiabatic or 6.5 Celsius per kilometer to include a moist convective adjustment. And so this gives you the essence of the problem of RCE, radiative convective equilibrium. And the point here to take away is that in our greenhouse atmosphere, by virtue of the fact that we have this bottom-heavy warming, this is constantly trying to act to destabilize the column, while convection is constantly trying to act to stabilize it and to mix out that instability, convective instability. So it in turn drives deep convection in the large-scale sense. And this is how we arrive at radiative convective equilibrium, which appears to be applicable, at least on the large-scale sense, in the tropics, whereby the temperature profile is something roughly close to moist adiabatic.
So how does the long-wave bottom-heavy warming compare with bottom-heavy warming due to surface fluxes, basically driving convection from below just by surface sensible heat exchange? And then is there not also top-heavy cooling the space that also destabilizes things?
Right, and that's an important part of it. The top-heavy cooling is what's trying to drag the top of this downward. So I think the surface fluxes are an intimate part of the problem. I think it's part of the way I think about this. But from the single column model experiment, they're able to do this sort of, it shows it nicely just by looking at this in terms of the temperature lapse rate. But yeah, the surface fluxes are in essence what helps keep you at a warmer state near the surface. Yeah. So on the large scale sense, long wave cooling promotes deep convection. And this is sort of our essential thinking of RCE in the tropics. So question number 2, is cloud radiation feedback important to storm scale dynamics? And so now we'll get into sort of the guts of the problem here. And I want to mention 2 lines of evidence for why we could assume that cloud radiation feedback might be important in the storm scale dynamics of tropical cyclones. And one in which there's been quite a mounting body of evidence on since Gray and Jacobs in 1977. in many studies since then is the diurnal cycle that we observe in tropical cyclones. And just to quickly touch on that here, so this is not the most exciting figure, but what it conveys is, I think, pretty exciting. So it's a very recent study where what they did was they composited over many dropsondes for all actually quite mature tropical cyclones in the tropical Atlantic. And what they're showing here is the diurnal variation of radial inflow in the boundary layer. So from 0 to 1 kilometer, and from a radius of the storms from 250 to 350 kilometers. And this gives you a variation with a peak inflow of about 5 a.m. and an amplitude of about 4 meters per second. And if you look at the scale here, so the values are negative for radial inflow, the amplitude of this diurnal variation is on a similar magnitude to the actual mean amplitude averaging over the day of the inflow. That's a very substantial variation of inflow. And that also, I'll mention, corresponds in time. So when the inflow is strongest is when we also observe rainfall to peak in tropical cyclones, or closely around that time. So the diurnal cycle is also observed from above, from satellite infrared temperatures. And what I'm showing you here are these so-called diurnal pulses in the cirrus outflow, as have been described by a few studies. And this is sort of a schematic I've drawn up, which is based on some modeling results of how the circulation changes in a tropical cyclone. And the point to take away here is that what's going on in the lower atmosphere, in the lower troposphere, is not necessarily what is going on in the upper troposphere, versus the time of day. And the top-down view is giving us a very nice depiction of these diurnal pulses. But now, with these boundary layer observations, we're trying to get a better handle on what's going on in the lower atmosphere. So the takeaway point here, however, is that the diurnal cycle is evidence that tropical organized convection is highly sensitive to radiative forcing. Because fundamentally, these diurnal changes in the TC, or in any case, organized convection in the tropics, is fundamentally driven by cloud-radiation interaction. So the next line of evidence for the role of cloud radiation feedback comes from so-called, what I'll call RCE World. So these are a set of idealized simulations which have been run by a large variety of groups, and they simplify the atmosphere, and by simplifying it, they highlight the role of radiative feedbacks in the climate system. And I'll give you an example of what that looks like here. So if you run a model, take this one just for an example. So this is a 6,000 by 6,000 kilometer model. It's very coarse for resolving convection, so we call it's grayscale convection permitting model, but we don't run a convective parameterization. You impose periodic lateral boundaries. There's no initial flow, no land, and the key here is that we impose interactive radiation, so it's fully realistic radiation. And so you start out, and long-wave cooling from the atmosphere destabilizes the column in sync with surface fluxes. And what you notice is that you quickly transition, I'll reset it here for you. You quickly transition from a state of popcorn convection scattered over a very large, scattered very randomly throughout the region, to very highly organized situation. And because we do this in a rotating framework, on an F-plane in particular, these take the form of what look like tropical cyclones. I can't stress enough how idealized these simulations are, as I show on the right-hand bullet points here. But the point here is that this couples to a discovery we've made in the last recent decades, is that the RCE system, we think, is unstable to large-scale overturning motions. So in essence, you develop overturning motions whereby you have large-scale subsidence in these brown regions, which are dry regions in terms of precipitated water. Sorry, I forgot to mention what we're looking at here. And upward motion inside of the tropical cyclone. And this is what's been termed self-aggregation, as studied by a number of people who've come before us. And so what's very interesting about this is that this RCE instability, this development of these sort of synoptic scale overturning motions, seems to be very keenly tied to interactive radiation. And to give you an example of this, so I'm taking this from another recent study where they also do this rotating self-aggregation here. So I'm showing you here a histogram of precipitable water along the x-axis. So this is considering the entire model domain, starting out from sort of a homogeneous initial condition, that's sort of the popcorn convection stage. And the development of a TC, the self-aggregation process, is shown here sort of by this arrow as you develop more moist columns, and then time progressing on the y-axis here. And this happens over quite a long time scale. So again, this is not realistic in the context of how quickly tropical cyclones develop in the real world. But the interesting thing is the sensitivity experiment, whereby when you remove radiative feedback and they do so by horizontally averaging and flattening out horizontal gradients in radiative heating at every time step. This dramatically slows the process of TC genesis. And this has been shown by a few other studies since then, confirming this result. It wasn't a spurious result, we think. So radiative feedback is critical to accelerating TC genesis in these idealized frameworks. And something I'll mention here is that radiative feedback is dominated by the cloud radiation forcing. And this is what we'll get into here in a moment. So let's step into a cartoon world. So idealizing the crap out of our already idealized tropical cyclone. So you can imagine sort of an average over convective region here and an average over a dry region here, right, where you may have some shallow cloud. Right? So on the right-hand side, if you plot a profile, vertical profile of the radiative heating, which we'll call QR, it would look like so. So you would have some relatively flat radiative cooling throughout the column in this region where you can presume is sort of large-scale subsidence. And the profile will look dramatically different in the area where you have a lot of deep convective cloud. And we can further sort of separate these two things. So the cloud radiation forcing, what this is taking a difference between the total radiative forcing, so the actual QR profile, and you can imagine recalculating the radiative flux profile with a clear sky. So removing any hydrometeors, removing the cloud, and calculating that radiative flux profile. So the clear sky, both here and here, might look relatively similar as compared to the cloud radiation forcing profile. This red dash profile has this profile as shown here. So a very top-heavy cooling and this bottom-heavy warming. And this bottom-heavy warming here has been termed for a long period of time the cloud greenhouse effect. And I think that's sort of a nice way of thinking about it that brings out this idea that it is a warming of the lower troposphere and enhances the upper level cooling. So you can imagine two consequences of that, which we'll get into in a moment here. So these two regions in reality are coupled, right, by virtue of transverse circulation. So you might have average upward motion in the region of deep convection and subsiding motion in the clear region here. But the interesting thing to think about here, again, going back to the very first slide, the fact that latent heating is much, much larger than radiative heating, this circulation to first order is driven by latent heating. But the question, nevertheless, is to what extent cloud radiation forcing, this red profile, which is several Kelvin per day, might affect this overturning transverse circulation. And by affecting this circulation, affect the TC development process. And this could happen one of two ways that we consider here. So hypothesis one would be the direct influence on the transverse circulation. So that's sort of exactly as shown here, where by virtue of this bottom-heavy warming, so the cloud greenhouse effect, the trapping of Longwave by the deep convective cloud, enhances the upward motion in the region of the convection. Or if you consider the vertical gradient in this profile, the fact that you have this top-heavy cooling and bottom-heavy warming here, you can imagine, again, going back to this idea of the greenhouse effect, leading to a destabilization of the column in sort of the lapse rate sense. Right? So the direct influence on lapse rate, and then if this influences lapse rate through this forcing, that will in turn invigorate convection and invigorate this gray arrow, right? So what does the radiative forcing actually look like? And this is now segueing into the simulations we'll actually dig into here. So this is an azimuthal mean cross-section around a precursor tropical disturbance. So there's no eye wall circulation in here, there's no vigorous surface circulation. This is sort of an early predecessor storm that may develop into a TC. And I'll describe the details of the Whorf model simulation in a moment here, but just sort of for the thought experiment. So this is the cloud radiation forcing, sort of as I've just shown in a cartoon sense, averaged over 48 hours. Now you can imagine separating this out into the long wave and into the short wave. And what you notice immediately, and sorry, I again forgot to mention what I'm showing here. So the radiative heating is in the shading, which you probably made out for yourself. And the contours here are the mass stream function in this framework. So what you immediately recognize is that the long wave cloud radiation forcing dominates the total cloud radiation forcing, right? So that's where fundamentally what I'm getting at here is from day-to-day time scales, averaging across the diurnal cycle, the long wave forcing dominates this pattern, right? If you look at the short wave, it's much weaker amplitude. You also notice that it has in some sense, the opposite vertical structure here. Now, on the other hand, if you do this time average, sort of a 3-hour time average centered around local noon, that heating is huge. And that's the absorption of shortwave in upper-level anvil clouds. And that does indeed affect the circulation. It does indeed affect the convection. But if we're interested on day-to-day timescales, what we first want to draw our attention to is how this is affecting the development of the TC. Since when you average over 48 hours, the total cloud radiation forcing is dominated by the Longwave. So that's what we'll sort of zero in on here. So getting at these two hypotheses, the approach here, these large domain WRF experiments that we've run based on two classic events, I'll sort of mention what I mean here. So case one, Major Hurricane Maria, which reached Category 5 on the Saffir-Simpson scale, and then Super Typhoon Haiyan. And I'll mention here that we've done the majority of our analysis based on Maria, and we looked at Haiyan for the sake of trying to examine whether we're getting potentially spurious results looking at one case. Looking at a second case at least helps us rule out that the role of spurious results. So then I'll mention here, so I say these events are classic. And what I mean by this is that in a statistical sense, in large-scale sense, there was warm sea surface temperature and weak vertical wind shear, and sort of the key ingredients in sort of the Bill Gray way of thinking about things that would lead to an intensification of a tropical cyclone event, a development, and then rapid intensification later on. And as I'll show you, we're able to reproduce these in these WRF simulations. So this is the model domain we use for both of these simulations. So the innermost domain is the red box here, covers the majority of the tropical Atlantic. And the reason we do that is because I don't want to use a moving model domain, because weird things happen at the edges. And if we're interested in testing the role of specific physics, I don't want weird things happening at the edges affecting sort of the fundamental inner core dynamics of the TC. So we use these large domains. They're fixed in time. They're non-moving. We run these simulations for about a week, and the idea is that at the start of the simulation, the precursor disturbance moves into the domain that eventually becomes Hurricane Maria or Typhoon Haiyan, moving into the domain at the early part of the simulation. And then we fully are resolving, fully representing internally in that innermost domain the actual intensification event. So we're doing a cold start from GFS. So that's at a 1/4 degree grid. And it's worth sort of emphasizing here that we're not interested in specifically a forecast. We're not doing a forecast test, right? We don't necessarily care to some extent if the details are different in the storm, but to the extent that we can represent the large-scale evolution of the TC, for example, its track and its intensification in response to the large-scale, favorable large-scale environment, that's what we're interested in. So we don't do data assimilation, and this would also, doing the DA would make it difficult to do our physics sensitivity tests. So, and I mentioned here some of the physics that we use. So radiation, and I've tested with some of the different schemes here. Radiation we're representing with RRTM for long wave and the Duty a shortwave scheme. And then the microphysics we're using the WRF 1 single moment scheme. And I've tested the double moment scheme. I'll just mention that here. You could ask me later on if you're interested in understanding what the sensitivity is, but in any case, the results so far have been robust to any of these sensitivities we've done. And I'll also highlight here that SST is fixed to the initial state, which would be a source of error probably in a forecast context, but we don't necessarily care about that for this case. So, getting at the tracks now. So I'm showing you the best track in the gray here, so that goes off the chart here. And I'm showing you, I'll describe sort of what the small ensemble of simulations is for Maria and then Haiyan on the bottom. But the point to take away here is that the model TC tracks follow very similar tracks to the actual TC Maria in the gray here, right? There are some differences here, but by and large, we could feel pretty safe to say that the model TC that we simulate is representative of the precursor disturbance and the large-scale steering flow and so forth of the real event. So it has the identity of Maria, if you will. A little bit different for Haiyan here. It has a little bit farther of a northward track, but one point I'll emphasize here is that the tracks of each of the individual sort of our small ensemble are at least self-consistent here. But I would say this is pretty similar to the real track. And one thing I'll mention that'll show up better on the next slide is that there's a delay in intensification, which we've speculated is due to the fact that we're spinning up from 1/4 degree grid onto our 3-kilometer grid, so we're starting out with essentially no convection on our grid scale. But nevertheless, we followed a similar track here. And as I'll point out, the intensification looks, we get a dramatic intensification that's quite representative of the real cases. So I'm showing you animations here of outgoing long-wave radiation, and I'll just let these play through for a moment. This is only on the inner domain. Step them over. So you can see how coarse it is at the initial state, right? And I would say that in the very beginning, it's very hard to identify anything you would call, like, that's the system, right? It really spawns sort of out of something you potentially can't see that's probably only in the vorticity field, perhaps not showing up in the cloud in the very first time steps. But nevertheless, by the end, we get landfalling TCs and intensifying TCs that follow the real tracks very similarly. And the intensity of them both reach category 4, so a little bit weaker than the real cases. So when I show these in this sort of framework, just to point out the size difference of Haiyan, which is something that's quite characteristic of West Pacific tropical cyclones. But both of these cases have the appearance of major TC events. So I'm showing you time series here of the intensification of these events in terms of maximum surface wind speed, minimum pressure, and integrated kinetic energy. So this is integrating essentially the 10-meter wind speed over a certain scale of radius. I think I do this over 800 kilometers, and it's essentially characterizing how large the scale of the intense wind speed swath does the storm have. So you'll be able to compare sort of the scale of each of the simulated storms by comparing the IKE curves here. So again, as I mentioned before, you see this delay in intensification in the best track, which is dotted here. But we capture rapid intensification, and we end up with a TC that peaks at 63 meters per second, at least in terms of instantaneous maximum wind speed. The delayed development here, again, we speculate that this may be due to spinning up from the initialized, from the GFS quarter-degree grid. But that's, again, I'll emphasize, it's speculation at this point. So this small ensemble I've run, and this is trying to get at the role of cloud radiation forcing. So what we do are these various tests, NCRF star H, where the star is a certain time of a model restart. So we start a restart from the control, where we make clouds, so we do the drastic test first. We make clouds fully transparent to long wave and short wave. Again, something that we typically treat clouds as in terms of our toy models of tropical cyclones. And we'll do this everywhere on this innermost model domain. And I'll point out here that we make the clouds transparent to long wave and short wave, and this means we've removed the cloud radiation feedback. But I'll point out that the clear sky long wave and short wave is still retained everywhere, such that in the clear sky regions where you don't have deep convective cloud, the radiation isn't really changed from what it would be in the control case. So we'll start these, we do these restarts at 12-hour increments backing up in time. So this restart is started here where this vertical hash mark sits. And you can see this restart is done roughly around the time of rapid intensification starting. And you can see you've lost on the order of 20 meters per second of intensification, and a slightly slower, although it's kind of an abrupt intensification rate. If we keep backing up in time, we get sort of a pattern showing up in each of these curves, in maximum wind speed, wind pressure, and integrated kinetic energy, until the point where we're at this NCRF 36H curve, this latest curve, where I would argue that there's very little sign, or no sign, in fact, of TC development. So removing CRF slows or prevents TC intensification. And an interesting finding here is that it appears to be a time-integrated effect. If we do this very late, we still reach an intense tropical cyclone. If we do it a few 12-hour increments earlier, no sign of development in NCRF 36-hour. And then now showing you the tests that we did for Haiyan. We repeat a couple of these tests to demonstrate that we get a very similar result. So the intensification is also delayed compared to the best track, but we end up with a category 4 TC. And when we remove the cloud radiation forcing, back here at this earliest time step, no sign of development. So Haiyan, we feel, is equally sensitive to cloud radiation forcing. So now ruling out, or ruling in, the particular role of long wave cloud radiation forcing. So we do this other test now, which is identical to NCRF 36H, but where we retain the long wave cloud radiation forcing for a radius inside of the TC. So for radius less than or equal to 600 kilometers, we've retained the long wave CRF. and we linearly ramp it down out to 800 kilometers. So outside of the TC, we have only the clear sky, long wave, and short wave everywhere. And then shortwave CRF is excluded everywhere. So the shortwave is only the clear sky. Does that make sense? So the test here is where we've only included long wave cloud radiation forcing and only in the vicinity of the TC, so that we could rule out spurious effects of the fact that we made clouds transparent everywhere in our large model domain. Long wave CRF follows the control remarkably well, and in fact is a little bit more intense. And this speaks to the fact that if we included shortwave CRF, it would bring that intensity down very slightly. It has virtually the opposite forcing of the long wave CRF, except much weaker. So it's a slightly stronger TC, but by and large, it very closely follows the control. So from this, we infer that long wave CRF is critical to TC development in RI in these two cases. And we haven't repeated this particular test for high-end, but we imply here that we would end up with ultimately the same result. So putting this in the view of a wind speed history map, so in the control case, removing the cloud radiation forcing at 84 hours, 12 hours earlier, 12 hours earlier, 12 hours earlier. So the lowest on the scale here is tropical storm strength, and then category 4 is right around here. So you all but kill the TC, but then add in the CRF and the long wave again, and you get back to the control, essentially. So what does this cloud radiation forcing actually look like? And this should look familiar now. This is essentially what I showed you earlier. And instead of actually showing the CRF, what I'm showing you here, this is the total long wave heating where I've subtracted a domain averaged vertical profile. So in essence, it's bringing out the pattern of the cloud radiation forcing. So you can call that the radial anomaly long wave forcing. And what you notice is that this is the NCRF 36-hour case where we've removed cloud radiation forcing. The long wave forcing is quite flat horizontally, radially. It has very weak gradients horizontally compared to in the case of the control when we include long wave cloud radiation forcing. Right? And then looking at the transverse circulation, we can see that this is much weaker than the NCRF 36-hour case. And that's implying that the deconvection is much weaker in this case. And we've looked at the latent heating and confirmed that. So, yeah.
Can you eyeball those two diagrams and say it's roughly twice as weak? Or half as strong, I guess? Just thinking about the gradient of the stream function. Is that fair, or is there more to it than that?
I mean, my eyes would guess about the same.
Okay.
But,
so.
yeah.
Okay.
Yeah. But what I would mention here is that we haven't been able to rule out yet, or say with any certainty, that this forcing is directly driving this transverse circulation, because it can work, again, through invigorating convection, and then the latent heating drives this circulation, right? That's sort of a key conundrum here we've got to deal with.
Oh, yeah, okay. I'm glad I asked my question.
Yeah. So we'll look at some CFADs. So this is contouring frequency by altitude diagram, and it'll probably be easier to understand what I'm actually showing once I actually show it. What we're trying to find is identifying key differences between the control and the NCRF tests early on in the life cycle of the storm. So again, before there's a strong surface circulation, before there's an eye wall, in this early life cycle period, averaged over this time scale. And we're sampling to create this frequency diagram. It's a histogram of sorts, sampling the native grid output within a specified radius. And I'll just mention, to preempt any potential questions on this, so I've played around with where we're actually sampling this, and it's remarkably insensitive, the results I'm showing you in a moment here, by and large. So CFAD's of vertical motion. So what I'm showing you here is the control on top, and then the differences between the control and the two NCRF tests in the middle and bottom, just to show that you get essentially the same result in both of these tests. So the difference is calculated as shown here. So in terms of vertical motion here, so it's a histogram with vertical motion along the x-axis, right? So the center line is the zero line, so zero vertical motion, upward motion on the right, downward motion on the left, okay? And pressure on the y-axis. So when you look at these differences here, what we're seeing is that the reds indicate more frequent, stronger convection in the case of the control. And that gives us the reds in both of these cases. And the difference is larger for the NCRF 36-hour test. That makes sense, right? And you also notice that there's a particularly large bullseye around cloud top, which we think is due to the cloud top cooling. So, yeah, that's what I mentioned there. Now we do the same thing in relative humidity, so with 100% over on the right-hand side here. So the control pattern and then the differences again, where here the reds indicate a more moist, lower free troposphere in the case of the control. And you see even a more pronounced difference by comparing the control in the 36-hour test, where you have a more commonly saturated troposphere and a more moist, lower free troposphere in the control than in the NCRF case. And something I'll give you sort of a not shown here. We've done this trying to identify lapse rate differences by calculating the lapse rate and trying to see if one is more unstable than the other to inconclusive results. And I can sort of say more on that later on. But I just want to mention, we've tried, that was actually one of the main intentions of looking at CFADs in the first place. So we haven't been able to identify which of these is driving things yet. So let's try to get at that. So one thing we can do for starters, since we're imposing the long-wave cloud radiation forcing in this LW-CRF test case, test simulation, we can also say, okay, include the long-wave cloud radiation forcing inside of 600 kilometers, but also just exclude this cloud top cooling. So only include what's going on here and what's going on from here downward. And likewise, we can select sort of certain aspects of this cloud radiation forcing and remove certain patterns of it. So that's what we do here. And I'll highlight these different blue lines here, which are all of these tests. So X-cool here, we've completely removed that cloud top cooling signature above 280 hectopascals. It's a very little difference from the LW-CRF test, or from the control, suggesting that, this was a major surprise to me, that there's a negligible impact of the cloud top cooling, implying that it's the warming beneath that level, right? So this is not completely conclusive against hypothesis 2, the lapse rate feedback, but it certainly doesn't support it. Now we remove only the PBL warming. Let me back up again here. So now we include all of this and we remove only that. That's a pretty substantial impact. So now we've dropped about 20 meters per second. But what if we do the opposite and only include the PBL warming? An even weaker TC development. So much weaker in fact, and suggesting that this mid-level warming is also vital. So both this mid-level warming in the free troposphere, and it tends to have a peak, which I can say more on a little later if anyone is interested. But this boundary layer warming appears to be important, but it's not the only critical aspect of it. It's this entire pattern of warming, we think, that's important to this, to these differences here. So the next thing we can do is take this warming and diagnose the circulation that would be balanced, directly balance this radiative forcing alone. So we do the Sawyer-Elias calculation, and that's courtesy of Hugh Willoughby was provided the solver code for this. And the benefit of this is that we can impose the heating. Let me back up here. So we can, using the Sawyer-Elias calculation, we can impose only the radiative forcing, see what the circulation is directly due to that. We could only impose the latent heating, and so on. And we can add these two things together. So representative of the early time period of the TC, we impose a broad, weak vortex based on that time period. So it's a very broad radius of maximum width of 200 kilometers with a Vmax near the surface of 9 meters per second. And then we, again, as I just mentioned, we specify this external heat forcing that the circulation will balance. So the solutions are shown here. Radial flow on the left and vertical flow on the right. So as you would expect, coupled to the cloud radiation forcing, where you have cloud top cooling, this will actually drive downward motion. And you'll have a coupled radial sort of circulation like that. And as you would expect, where you have warming, you have upward vertical motion, right? And this will drive low-level inflow. But I'll draw your attention to the fact that in order to include these contours on both of these panels, I had to change the uniting. This is 0.1 centimeters per second here, with a maximum of about 0.3 due to the radiative forcing, with a maximum of about 14 centimeters per second in the case of the latent heating. Again, emphasizing the fact that from a scale analysis, you would rule out the role of radiative forcing and say that the latent heating clearly dominates in driving this circulation. But wait, let's take this one step further. Let's ask the question, due to this weak circulation, which is always going on in the background as long as there's cloud here in this developing precursor disturbance. How long would it take this weak sort of background circulation that's operating sort of within this cluster to saturate the column? So we do a simple calculation, which requires a calculation of LCL height, and taking this vertical motion that we get from the Sawyer-Eliason diagnosis. And you can calculate a time scale of saturation just by that ratio. And of course, we're only interested in here what would be doing the saturating, which is the upward motion part of this, right? And what you see here, so I'm showing you in the shading relative humidity. So as you would expect, relative humidity is greatest on the right. These contours here, I hope you can see the values. But generally over the majority of this region, you have about 24 hours or less, with a contour of 18 hours here, reaching down to nearly the surface, 12 hours here, and this region 6 hours here. So 24 hours or less in general, and as low as 6 hours. So in other words, what we're saying is that it only takes on the time scale of a day for this weak background circulation to help saturate the column. If you remove the cloud radiation forcing, you remove this weak background ascending motion, which is helping to saturate the column. And recall that NCRF 36-hour, recall that it appears to be a time-integrated effect. In the NCRF 36-hour case, which was roughly 48 hours prior to rapid intensification, we saw no sign of development. So that's roughly 2 times the time scale of this saturation here as diagnosed from this calculation. So, hypothesis 1 is supported, and in particular what we think is going on is that this slow lifting due to the long-wave cloud radiation forcing, in particular the cloud greenhouse warming, right? So this warming component down here promotes convection by helping to saturate the column. H2 is not supported, and in particular the test we've done is sort of chopping off this cloud top cooling, and it seemed to have virtually no effect on the TC development, or suppressing the TC development. So that doesn't support H2, but I would say we also can't strongly rule that out either. So cloud long wave feedback we find from these experiments, and for these 2 cases, for these particular model experiments that we've run, cloud long wave feedback is critical to TC development in RI. To the extent that these 2 TCs and that our model experiments are representative of a broad population of TCs that develop around the world, cloud radiation forcing might be a vital thing to the amount of TCs we see globally, and in particular major TCs, the strongest TCs. Now I would not sort of extend myself to say that these findings should apply to cases of, say, strong vertical shear, very dynamically forced TC development cases. But cases under weak wind shear, which these 2 TC events are representative of, these findings might apply. I think there's an important forecast opportunity in considering these findings. So TC intensity prediction, so I think it's probably general knowledge in this room, especially concerning rapid intensification, remains a really important forecast challenge. Our complex models continually struggle to properly forecast TC intensity and the development of TCs, especially rapid intensification. So I would hypothesize, if we needed yet one more reason that we have to improve microphysics in models, improve microphysics, improve the coupling with radiation and the feedback between radiation and microphysics, improve the prediction of TC genesis and RI. And I would put money behind that hypothesis, but it is a hypothesis. Thanks very much. Yeah, John.
Very interesting. I'm bound to ask a naive question here. I always do. But let me think about the tropical cyclone problem. You can use a diagnostic like the Sawyer-Eliason equation to figure out radial and vertical motions and all that. How can you expand the thinking that goes that went into creating the hypotheses in the first place to other problems of tropical convection, like the Madden-Julian oscillation, like the double ITCZ in climate models? Are there some things here that can translate into there and add some or give us some insight about how these things work for the MJO, or how the double ITCZ shows up in models as an error?
So in the context of the MJO, at least, I would say that the radiative feedback really shows up clearly in terms of phasing with the strongest sort of, when you have the strongest convection, you see the strongest radiative forcing anomaly. So it really would suggest that, sort of striking the analog with the TC, that in a strong TC, situation, it would show up that the radiation is the key sort of driving force to that, as opposed to the latent heating, for example. Well, that's when you look at things in terms of moist static energy. That's your main moist static energy source. In terms of developing an MJO event, so MJO onset and initiation, I'd be speculating.
We encourage that, yeah.
Yeah, okay. The one thing that seems apparent to me in the case of the MJO is that, every case could be different. A lot of them could be different. And it seems clear to me, I may be spending too much time around Paul Roundy, but that there's a huge extratropical influence. That there's, obviously an outward from the tropics influence, but his group's work has even shown that some of these MJO events kick off an extratropical influence that then comes back and helps with MJO initiation for the next event. And then similarly for the circumnavigating MJO signal, after it decouples from convection and is coming across as a dry Kelvin wave across Africa, or what looks to be closer to a dry Kelvin wave over Africa, you see this sort of difluent flow in the upper troposphere come across the Indian Ocean, and this helps trigger convection. And it seems hard to rule out that this dry dynamical signal is important to triggering the next MJO event. But in terms of once you have an MJO event, it seems clear. I think there's growing evidence that the radiative feedback is helping to keep that strong MJO event there.
Okay, so
I'm not sure about the triggering.
It can tip it into sustenance of something that may have been sprouted.
Yeah,
Okay.
that might be the best way of thinking about it. Yeah.
Okay.
Yeah, Jim?
Great stuff. I think about genesis and rapid intensification differently because I think some of the physics are different and some of the environmental requirements are different. The idea of saturating the column to me makes very, very good sense for genesis, but it's not as clear to me for rapid intensification, particularly if we have a mature vortex at that point that's already pretty much saturated.
Yeah.
So how does that play into RI? Clearly it's doing something.
Yeah. It's possible that this could involve feedbacks through the rain bands, for example. And so I've shown, I've emphasized largely in all the figures I've shown here today, sort of azimuthally averaged, phase space. If you sort of focus on a particular quadrant where there's the strongest convection, where you have a very vigorous rain band, these cloud radiation feedbacks are much more vigorous, in fact. So it might suggest that the axisymmetric viewpoint only takes us so far, and that there's more complex dynamics going on. And yeah, I fully grant that we have a lot more to try to understand those dynamics. So yeah, I appreciate it.
I'll ask another one if no
Yeah.
other hands are. So you showed, that was a 2020 paper by Zhang et al.
Yeah.
That I wasn't aware of yet. It looked
Yeah.
fascinating. But you showed a very, very large clear signal in the radial inflow, a diurnal signal, right? Now, presumably, that should project onto the primary circulation, but I don't think it does. I'm not sure what data they use, whether it's flight level data, but I remember looking at this problem, and I didn't find a very large signal in the primary circulation. So I'm wondering how we reconcile that.
I'll pull it up.
Oh, excellent.
I should be able to pull it up quickly. Let's see. Yeah, so I think it's just like an early online release at this stage. Yeah, so they've looked at the tangential flow as well. Let's see here. These are the thermodynamics, and here's the tangential flow. Maximize that too. And then they calculate. So they do an average over 0 to 6 local times. So that's when boundary inflow peaks here, and then an average over the afternoon, and then take the difference of those. So you see differences on the order of up to say 4 meters per second there. Yeah.
So maybe it just, I used best track data that was anchored
Yeah.
to recon, it looks like they're using dropson data, so.
Yeah.
They're probably just better data is what brought it out, that's really interesting.
Yeah, so they've used a large, I think on the order of like 2,200 dropsons from all the recon flights. Yeah.
That's great, thanks.
Yep.
So I could have a follow-up to Jim's question, which is, you showed that the shortwave forcing was overall 24-hour average small, but that it did oppose the long wave and peak.
Yeah.
Is that shortwave forcing part of this diurnal modulation?
Yeah, absolutely. And I would have loved to get more into that because I really love that subject. But I would have taken 2 hours of your time if I haven't already. Yeah, we think that this shortwave, so as I mentioned, let me show the actual model patterns here, which is a bit more realistic than the cartoon. If you do that average centered 3 hours right around local noon, you've got heating on the order, it may go off the scale here, on the order of 4 Kelvin per day. And this, on one hand, we think is, so this top-heavy heating, we think on one hand is really important for suppressing deep convective activity because you're getting this upper-level heating. But what's also interesting is that it's apparently lifting the circulation, and you might actually be able to make that out. It's difficult to see at the upper levels here, but when we've composited over time, in idealized simulations at least, we've seen what I've sort of schematized here is that you get this more top-heavy circulation. So this schematic's based on a non-rotating framework, but by and large we see similar results in the TC outside of the eye wall in particular. So we get this more top-heavy circulation where down here the mass flux and the overall upward motion is much weaker during the daytime hours. And we think that's really strongly driven by this upper-level shortwave heating, shortwave absorption in the anvil clouds. Yeah.
Something, technique I'm familiar with in large-scale climate communities, this idea of cloud locking or cloud fixing, which is really similar to what we've done.
Yeah.
But instead of removing the entire effect of the long wave or short wave, use a time mean field that long wave or short wave cloud radiative effect in there. And what that does is it allows you to take a look at something even more subtle, which is the effect of the variations in long wave or short wave without that mean. And I was wondering if you've thought about any of those kind of cloud circulation interactions that come from the effect of the clouds being influenced by the circulation, and using that kind of technique to hold it fixed and not allow this. So it might get at a different kind of mechanism, something more subtle, but maybe more important for the actual mechanisms involved with rapid intensification.
Yeah, yeah. I haven't thought much about that from the context of these WRF simulations. I mean, one issue we'd have to deal with in sort of the realistic framework is the TC is, you know, it's got this motion. So that would be tricky. But yeah, I see what you're getting at here. So actually, so I take it back. I think I have thought about this, but just not sort of worded the way you put it. So one thing I'd really like to try is, I won't show it. You've already seen the cloud radiation forcing. So we have this azimuthally averaged cloud radiation forcing. What I'd like to do is run the NCRF test where we completely make the clouds transparent, but then impose the axis-symmetrized, so the azimuthally averaged cloud radiation forcing following the TC. So that then we're essentially testing the role of asymmetries and potential feedbacks, on a local scale with respect to rain bands and so on. And it would also help to check us on if this axisymmetric thinking in general is sort of on the right track or not. Yeah, so I think that's in some ways aligned with what you're suggesting. Is that right?
Yeah.
Yeah, okay. Yeah, Dave.
So the peaks you showed from the WRF and the heating output in the long wave are kind of in the mid-levels, near the freezing level, and the upper levels, which would suggest likely changes in stratiform rainfall, stratiform clouds, or annual clouds in terms of relating that long wave heating. So do you see significant changes or differences in the vertical distribution of cloud water mixing ratio or ice water mixing ratio between those different runs at like kind of correspond to those peaks that you see like at 6 or 500 millibars.
Yeah. Yeah, and I mean, for those of you who study like mesoscale convection, you probably noticed, Angela, I'm looking at you, there's a bright band here that shows up. That's, yeah, like a really clear signature of like pronounced stratiform rain fraction, I think. In terms of the actual microphysical amounts, I haven't looked at sort of like whether there's a different distribution of, say, convective versus stratiform or something like that. In general, I guess what I can say is at least from looking at the standpoint at latent heating, there's substantially weaker latent heating in the NCRF tests, and that's what's driving essentially the weaker stream function, the weaker circulation overall. So there's less cloud by virtue of that, but I haven't looked at it sort of more deeply than that yet. Yeah. But yeah, this bright band feature is really intriguing, and this is especially what really flares up if you focus on a particular quadrant where there's more convection in that quadrant. You see this, right around the 0 degree C level, where there's probably a lot of cloud bases. Yeah.
You mentioned something about rain bands. I always ask hurricane people, what's the role of the rain bands? And maybe this is part of the answer?
Oh,
Because why do the storms have rain bands?
why aren't they all annular?
Yeah.
Yeah.
We model them as annual. How come they have rain bands?
Yeah. Yeah, everything we've looked at is sort of an annular viewpoint, yeah, in essence.
They
Yeah.
must do something.
Yeah. I will not speculate on that.
Okay.
Sorry.
Well, we'll talk about it something. Because I don't know the answer. I have no idea, but I'd like to know. I've asked Jim a million times.
And if we believe Lane Schubert, it's just PV filaments from mixing in the inner core, flying out. Just like that, you throw your arms up.
Yeah. They must do something.
So why do they stop doing that when it's annular?
Because, well, the hypothesis in that et al. Was that the width of the eye wall becomes barotropically and barochronically stable, and you stop getting those mixing events for a while. I don't know if this is right, but those are the hypotheses for it.
Okay. Mhm.
I wouldn't bet money on it.
I wish I knew more
Fair
about
enough.
this stuff.
All right.
Okay, well, let's
Well, thank you
take
guys again.
things one more time.